everyone, welcome back to Quantitative Reasoning, and today we are in section 2.2 and we'll be talking about subsets. So in this section we will learn to recognize subsets, and we will learn to use the notation for a subset, and we will also learn to recognize proper subsets and use the notation for a proper subset, and then we will learn how to determine the number of subsets that a set can have. So here we go. So first, let's talk about what a subset is. The symbol for is a subset of is this symbol that looks like an elongated C with a line under it. Of course, that is not a C, but that's kind of what it looks like. So this symbol is read is a subset of. Now, what do we mean by subset? Set A is a subset of set B, which we would write this way. This says A is a subset of B if every element in set A is also an element in set B. And it's important to keep in mind that a subset is itself a set, so it has to be treated like a set, and it has to follow all the same rules that a set has to follow. Now we also have a symbol that means is not a subset of, and that is just our subset symbol with a line through it, like that. And set A is not a subset of set B if there is at least one element of set A that is not an element of set B. Now, we can show that A is a subset of B by showing that every element of set A also occurs as an element of set B. On the other hand, we can show that A is not a subset of B if we can find one element of set A that is not in set B. So here is example 1. We're just going to practice using the symbols for is a subset of and is not a subset of. So we'll want to write the appropriate symbol in the blank to form a true statement. So here in part A, we have set A is the set containing 1, 3, 5, and 7. Set B is the set containing 1, 3, 5, 7, 9, and 11. So the question is every element in set A present in set B? And the answer is yes, and that means that A is a subset of B. So we'll put the subset symbol in the blank. Set A is a subset of set B. Then for part B, set A is the set of all elements X such that X is a letter in the word proof. So the elements of set A are P, R, O, and F. And set B is the set of all elements Y such that Y is a letter in the word roof. So the elements of set B are R, O, and F. Now the question again is, are there any elements of set A that are not present as elements in set B? And here the answer is yes, because the element P in set A is not present as an element of set B. So we would have to say that set A is not a subset of set B. And then part C says that set A is the set of all elements X such that X is a day of the week. So you can imagine that that would be the set containing Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. And then set B is exactly that. It's the set containing Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. And so every element in set A is present in set B, and that means that set A is a subset of set B. Now I want you to think about something for just a second here. We said that set A is a subset of set B because every element in A was also an element in set B. But we also noticed that A is exactly equal to B because every element in A is an element in B, and every element in B is an element in A. So if one set can be equal to another set, but at the same time that set is a subset of the other set, well, that means that every set is a subset of itself. So in set notation, we can say that any set A is a subset of itself. So set A is a subset of set A. You can visualize that this way. And then if we want to exclude the possibility of two sets being equal, that's called a proper subset. So if we know that set A is a subset of set B, and we exclude the possibility of the sets being equal, then set A is called a proper subset of set B. And that is written this way. It's the same symbol, but without the line underneath. So this is read, A is a proper subset of set B. So do you see the difference between is a subset of here and is a proper subset of here? And so you can visualize that this way. So if every element in A is also present in B, but there are additional elements in B so that the two sets are not equal, then we can say that A is a proper subset of B. So let's just go over it one more time. Here is the definition of a proper subset of a set. Set A is a proper subset of set B, which is written with this elongated C looking symbol with no line under it. So this says that A is a proper subset of B. If set A is a subset of set B, but sets A and B are not equal. So you may have noticed that the bar underneath the subset symbol kind of suggests an equal sign. It's very much similar to the difference between a less than symbol and a less than or equal to symbol. When we use the subset symbol that has the line underneath, it is possible that sets A and B are equal. They don't have to be, but they can be. On the other hand, if we don't have the lower line underneath, so if it just says A is a proper subset of B, that leaves out the possibility that A is equal to B. So let's practice using the subset symbol and the proper subset symbol in example 2. So it says in part A, the set A is equal to the set of all elements X such that X is a person and X lives in San Francisco. So set A is basically the set of all people who live in San Francisco. Now set B is equal to the set of all elements X such that X is a person and X lives in California. Now San Francisco is fully contained in California, so everyone who lives in San Francisco also lives in California. And so we can say that A is a subset of B. But we also know that there are more cities in California besides just San Francisco. So we could also say that A is a proper subset of B. The two sets are not equal, we know that for sure. So not only can we say that A is a subset of B, we can also go further and say that A is a proper subset of B. And now let's look at part B. The set A here is the set containing 2, 4, 6, and 8. The set B is the set containing 2, 8, 4, and 6. Now you can just look at these and tell that set A and set B contain all the same elements. And so A does qualify as a subset of B because all the elements in set A are present in set B. So we can say that A is a subset of B. But we cannot say that A is a proper subset of B because the two sets are exactly equal, and a proper subset does not allow the two sets to be equal. Now, in example 3, we're going to think about subsets in the empty set. So here, let's imagine that A is the empty set, and B is the set containing 1, 2, 3, 4, and 5. is it true that A is a subset of B? Well, let's kind of think through it together. The rule is that A is not a subset of B if there is at least one element of A that is not an element of B. But A represents the empty set, and there are no elements in set A. That means there are no elements in set A that do not belong to B. Therefore, set A is a subset of set B. And this shows that the empty set is a subset of every set. And we can also say that the empty set is a proper subset of every set except itself. So just to reiterate, for any set B, the empty set is a subset of B. And for any set B other than the empty set is a proper subset of set B. Now, one place that people get tripped up very frequently is the difference between the element symbol and the subset symbol. So let's think about what it means for something to be an element of a set and for something to be a subset of a set. Of course, you remember from section 2.1 that this symbol means is an element of. And today we learned that this symbol means is a subset of. Now remember that a subset is itself a set. So something that's not a set cannot possibly be a subset. We remember that sets are always enclosed in braces, and again, only a set can be a subset. So now think about the set containing 2, 3, and 4. We could say that 3 is an element of the set containing 2, 3, and 4. In set notation, we would write it this way. 3 is an element of the set containing 2, 3, and 4. But we can't say that 3 is a subset of the set containing 2, 3, and 4 because 3 is not a set. If it's not a set, it can't be a subset. On the other hand, we could say that the set containing 3 is a subset of the set containing 2, 3, and 4. And in set notation, that would look like this. The set containing 3 is a subset of the set containing 2, 3, and 4. Do you see how important it is that whenever we see the curly braces that we read that as the set containing? So that will keep you straight as far as the difference between the subset symbol and the element symbol. So the set containing 3 is a subset of the set containing 2, 3, and 4. But we can't say that the set containing 3 is an element of the set containing 2, 3, and 4. This set has 3 elements, 2, 3, and 4. It does not have the set containing 3 as an element. So although 3 is an element of this set, the set containing 3 is not. Okay, so example 4, determine whether each statement is true or false. If the statement is false, explain why. So part A says Leonard is an element of the set containing Leonard, Sheldon, Howard, and Raj. Okay, so of course that's true. We see Leonard in this set, so that statement is true. Part B says Canada is a subset of the set containing Mexico, Canada, and the United States. Now, Canada is not a set, so it cannot possibly be a subset. So we're going to say that statement is false because Canada is not a set. Okay, part C says the set containing 5 is a subset of the set containing 5, 7, and 9. So of course that's true because every element in this first set is present in the second set. So that statement is true. And then part D, the set containing 4 is an element of the set containing 4 and 8. That is false because although 4 is an element of this set, the set containing 4 is not an element of this set. So we'll say false, because although 4 is an element of the set containing 4 and 8, the set containing 4 is not. Now let's talk about the number of subsets that a given set can have. And so here we have 4 different sets, each with a different number of elements. And what we're going to do is look at the subsets of each of these sets and see if we can notice a pattern. So first up is the empty set. Now the point of the empty set is that it has 0 elements. And therefore the only subset that the empty set has is itself. So there's just one subset for the empty set. Now here we have a set with 1 element. So the number of elements is 1. If we list the subsets, well, the empty set is a subset of every set. So we would have the empty set, but also the set itself. So a set with 1 element has 2 different subsets. There we go. The number of subsets is 2. A set with 1 element has 2 subsets. Now here we have a set with 2 elements. So the number of elements is 2. The subsets of this set would be, of course, the empty set, but also the set containing A, also the set containing B, and then, of course, the set itself. And so the number of different subsets that we have here is 4. Are you starting to see a pattern? Let's see if the pattern holds up. When we have 3 elements in a set, the number of elements is 3. Now the subsets will be the empty set, the set containing A, the set containing B, the set containing C, and then we have to have every different subset we can make with 2 elements. So the set containing A and B, the set containing A and C, the set containing B and C, and then the set that has all 3 elements is a subset. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. And so if a set has 3 elements, the number of subsets is 8. So I hope you see a pattern. Notice that 2 to the 0 is 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8. And that's exactly the result that we have here. So however many elements a set has, 2 to that power will tell you how many subsets that set can have. And that's the formula. For a set with n elements, the number of subsets is 2 to the n. But now, of course, the number of subsets always counts the set itself as a subset. If you want to talk about the number of proper subsets, you want to exclude the set itself. So the number of proper subsets would be 2 to the n minus 1. So the number of subsets is 2 to the n, but the number of proper subsets is that same 2 to the n, but minus 1. Okay, example 5. Find the number of distinct subsets and the number of distinct proper subsets. So here in part A, we have the set containing A, B, C, D, and E. That set has 5 elements. So the number of distinct subsets for a set with 5 elements is 2 to the 5th power. You can do that on your calculator, but 2 times 2 makes 4, and 4 times a third 2 makes 8, and 8 times a fourth 2 makes 16, and 16 times a fifth 2 makes 32. And then the number of distinct proper subsets, it's 32, but we need to leave out the subset that contains all 5 elements. So for a set with 5 elements, the number of distinct proper subsets is 2 to the 5th minus 1, so 32 minus 1, so 31. Now in part B, we have the set of all elements x, such that x is an element of the natural numbers, and 9 is less than or equal to x, which is less than or equal to 15. So in order to use our formula, of course, we need to know exactly how many elements we're talking about here, so let's just make a list of all the elements of this set. So it's the natural numbers beginning with 9 and ending at 15. So the set containing 9, 10, 11, 12, 13, 14, and 15. That is 7 elements. So the number of distinct subsets of a set with 7 elements is 2 to the 7th. Now we already know that 2 to the 5th is 32. So 32 times a 6th 2 would make 64, and 64 times a 7th 2 would make 128. And then the number of distinct proper subsets is going to be 1 less than that because we need to leave out the subset that contains all 7 elements. So that's going to be 2 to the 7th minus 1, which is 128 minus 1, which is 127. And then finally part C says find the number of distinct subsets and the number of distinct proper subsets for the set containing all elements x such that x is an element of the natural numbers and 9 is less than x is less than 15. So notice this time we don't have the or equal to bars. So if x is between 9 and 15 but we can't include those two numbers, then our set would be the set containing 10, 11, 12, 13, and 14, and that's it. So here we only have 5 elements. So again, the number of distinct subsets of a set with 5 elements is 2 to the 5th, and that's 32. And then the number of distinct proper subsets would be 2 to the 5th minus 1, because we want to leave out the subset that contains all 5 elements. And that, of course, would be 32 minus 1, and that's just 31. And that's all we have today in section 2.2. So I hope this has been helpful for you, and I'll see you next time in section 2.3.